Hello everyone, I am Georgina Maldonado and I am the product manager for the Moses software. And I'll be giving this session. I have a video and I will be pausing the video when I need to actually show you a live demonstration of Moses. The majority of the video is about the jacket supports. In that video we'll be talking about gap distance and the final location. That's going to take up the majority of the video, and at the end we're going to take a few minutes to talk about the barge part of the analysis. So here is an artist's rendition of what the loadout is. It is a moving of the jacket from the right to the left in the picture, and you see the blue lines. That is the gap distance. On the upper left hand corner there is the commands that you would use in Moses. I will be using the commands that we ship with the automated installation tools. Maybe some of you all are familiar with those. The automated installation tools do loadout, transportation, upends, launch, and lifts. They do those. You set up your data in the beginning, and it has some automatic defaults you have to accept, but it will do those analyses for you and make up some structural load cases and give you some pre-formatted reports. Today we are concentrating on loadout. So as you see, the jacket moves from stages from the right to the left, and the jacket support is provided by supports on the launch legs. Okay, now many of these concepts will lend themselves to other structures. I just happen to be using a jacket with launch legs. One, because it's easier for me. So each one of these arrows is meant to be a support. And as a jacket moves, you can see that when a support is over the gap, that support is inactivated. So each one of these stages or events will load case. And Moses has the ability of making those structural load cases automatically for you. Now, in a perfect world, we would have the gap distance of length 0, and the barge would be as rigid as the key. The barge would be at even keel, and there would not be a need. Okay, but we don't live in a perfect world. So now we need to talk about these support conditions that result by the changes in as the jacket travels over the gap. So again, this is our loadout direction. Okay, for this analysis, our gap distance is 10 meters. Okay, so we're going to, at the first position, that's what I have here, you see that the entire structure is on the key. So all of the supports are active, and that was what the little section of the log file shows on the upper left-hand corner. Okay, so here is position 2. And you see those yellow lines where the gap is. You see that there is a set of connectors in the gap. Okay, and I'm saying it's a set because there is a port side support and a starboard side support. And so that is what the log file is showing us, the set of supports that is in the gap file, that is in the gap. So if we continue with our loadout, you can see that the arrows come and go as the jacket keeps traveling. And position 10, you're going to see that maybe the gap distance is a little short. For this analysis, a gap distance of 10 meters means that for position 10, all of the supports are active. Okay, so this essentially is the same as the jacket being on the key. Okay, however, we're going to be thinking like, well, is that really a load case that we want to be defining position 10, right? So your gap distance has influence on your load cases in that manner. And then if we continue all the way to the last position, on the last position you see that there's a possibility that 2 sets of supports are going to be in the gap. Okay, so depending on your gap distance, more than one set of supports. So that's why it's important to consider how big your gap distance is. Okay, so in this case we said, well, the yard gave us the 10 meters and that's what they measured out. But let's say that the project has told us that they want at least one set of connectors to be in the gap. Okay. Here is the artist rendition again. Okay, so let's go back to what the log file is showing us. Okay, in the lower right-hand corner, I am again showing this. It tells us which two nodes are in the gap. And I'm also showing a section of the log file that tells us the distance between the consecutive nodes. Okay, it was going to be too much writing to put actually the node names along the launch legs on this. So that's why I'm just putting that log file at the top. So you see for position 2, on the section of log file that's shown towards the bottom, it says 101 and 103. Okay, so the distance between it says 105 and 103. The distance between 105 and the next set of nodes is 6.1 meters. Okay, so that is why for position 2, we have one set of nodes in the gap. Okay, so now position 6. Okay, so position 6, now it says, and the gap is 205 and 203. Okay, so if we look at the distance between those nodes, we see that it is 7 meters. Okay, so again, we have a set of nodes that is in the gap. And then if we continue, we are next going to get to that position 10 that we talked about earlier, that we were wondering why there is not a set of nodes in the gap. And you see that for position 10, the distance between those consecutive nodes is 13. And so that is why we did not get a set of nodes in the gap. And then for the last two positions, we have something that is very short, 2.5. Okay, so that's what we're saying, that, wow, that's kind of a short. Two sets of nodes are going to be in the gap. Now, based on which nodes are in the gap, again, Moses will automatically make our structural load cases. Okay, so what about if the project has told us that they want to make sure that one set of nodes is in the gap for each event? So in that case, we can accommodate that request by increasing the gap distance. So what I'm going to do next is from 10 to 15. Right, so so for our position 10, remember our position 10 are the distance between consecutive. So when we increase our gap distance to 15, we should get that set of nodes in the gap. So here again is the sequence, and you will see, once I start it, at the beginning of the loadout sequence, in the beginning, actually two sets of nodes could be in the gap. Okay, so we are not only changing the structural load case for position 10, we're also changing the structural load case for those positions 1, 2, 3s, and 4s. And so you see here we're getting close to position 10, and you see that there is nodes in the gap. So here is, again, I'm going to do it with the arrows, and there is the yellow lines indicate where the gap is. And then when we get to position 10, we'll be able to see that the gap is big enough so that a set of nodes is in the gap. Okay, so on all of these, in that report that Moses shows with the log file, Moses tells us which node is at the bulkhead edge. Okay, position you are at. It makes a load case every time a node comes to the bulkhead edge. Okay, and I'm showing you how to change the options, and that really is about what the options possibilities are with Moses. I'm kind of just showing you how to use the tool. Okay, so what are the differences in reactions? Okay, so for our position 10 that we have been focusing on, right, so here's position 10 with the gap distance of 10 meters, and you see that there is support being provided, and therefore hopefully the jacket passes structural code check. But for when our gap distance was 15 meters, so here is the gap distance of 15 meters, right? Our set of nodes is in the gap. So if we were to compare the structural analysis of the 10-meter gap and then the 15-meter gap, we would see that there is higher stresses in the load case with the 15-meter gap. Okay, I am showing you part of the output on the upper left-hand side. And those of you who are familiar with Moses are probably saying, hey, she altered it. Okay, I did. This one report actually has a lot of data in it, and I needed to fit it into the screen. Okay, so here I went ahead and I separated the starboard side nodes to the port side nodes. And you see that those are the, I left the loads that are on the barge. You see under the column that says element, all of the elements start with B, meaning those are barge supports. Okay, because and you see also that the forces are only in the Z direction. So these supports only offer support in the Z direction. Okay, so that concludes the section for the focus on the gap distance. Now we are going to discuss the skid length and the final exposition. Yes, James.
We've just had a question come in regarding that gap distance. For loading over the stern and that onto the rocker arm, are we looking at, does the load transfer onto the rocker arm, or is it considered a larger gap?
Right. Okay, so as you see, right now I have that little arrow like right at the edge of the rocker arm. When I was an engineer, I would count the load getting on the barge once it passed the pin. Okay, because what we're going to do later on is longitudinal strength. Okay, and when you are given that section modulus for the barge, that the strength of the barge is actually from the bow to the stern, and the stern being the pin. Okay. Also, in the model that I have, when this particular model that I put into Moses, I did not put in, what kind of friction there is at the pin. Okay, I didn't put, if there's any type of separate support between the skid, between the rocker arm and the barge. Because you have control of what the gap distance is, and you have control as to when the loads are actually loaded onto the barge, you can certainly put this load as I'm showing it in the picture, you can put that as already being loaded on the barge. However, from my interactions with other engineers, most people wait until it crosses that pin before they say that it is on the barge. Any other questions, James?
Yeah, we do have another one that's just come in as I'm reading it. Is excessive heave on barge during the loadout process from key to barge considered? If yes, would a larger gap or joint displacement be included in different load condition?
Okay, can you say that again? I think there was actually two questions. I need to make it separated in my mind. I think those were two questions.
Is excessive heave on the barge during loadout process from key to barge considered? Is the first half.
Okay.
And then the second half is, does a larger gap or joint displacement be included in the different load condition?
Right. Okay. So by heave, I'm going to interpret heave as being there might be some wave activity, or because of how you are changing the ballast, you might be changing how the condition of the barge. So there might be a slight pitch or a change in draft. And sometimes you do want to change in draft, for example, to account for tide. Okay, so maybe your pumps are a little faster than what you had planned, and perhaps that is why you have some heave. Okay, to make these structural load cases, Moses does make the assumption that you have complete control over the barge, that you have complete control over the barge such that you are not going to change the draft or the pitch, and you are also complete control over the barge, that when you do your longitudinal strength calculations, you have control over the deformed shape of that barge. Of course, we don't want to break the barge, and of course we will be good engineers and try to keep that skid beam as level as possible. We're talking about such large weights. Of course, we are not going to, everything is not going to measure 0, 0, 0 deflection all the time. So that's the other heave that is possible, is because of barge deflection. Okay, so that was question 1. Okay, James, what was question 2 again?
Question 2 was, if yes, would a larger gap or joint displacement be included in different load condition?
Okay, so so if you have a larger heave, so the question to answer 1 was no, we are making the assumption that there is no heave for this part. So the larger gap, the gap is whatever you have typed into the command file. Okay, and as I keep saying, Moses automatically makes these load cases, and for example, here is the code check that Moses did for our load case 10. And you see under the column load case, it made up our name LOA vertical bar 010 for load case 10. And it'll do this for every one of those stages. Depending on, and of course, depending on your gap distance, right, you will change your load case. You can also do this code check with SACS. Okay, so perhaps that perhaps you are using Moses just to get the loads, and then you do the code check in SACS. Okay, and so now we are going to continue, and we're going to talk about the skid length and the final X location. And they are both in that same blue because I'm going to talk about them together because one influences the other. So when I was talking about gap distance, okay, I moved the jacket from the right to the left. Okay, and there is the indication of what the gap distance is. Now, I like for my x-axis to go from the right to the left. Okay, and because here we're doing a stern loadout, for the first part of the video, I had it going from the other way direction. Okay, so now, usually axis from the bow, and you see there is the length of the skidway. You see that it starts at the pin and it ends wherever the skidways end. And so if you have a final X location with a positive value, then it is measured in the positive X direction. So you see here how in the command file we used a positive value, and therefore it's a little to the left of the end of the skidway. Okay, so you might be asking, well, you know, this is a moderate-sized jacket. You know, my company works in very deep. What happens if my jacket is actually my barge? Or it could be also that my jacket is just longer than my skidways. So for that, you would use a negative distance. For example, here, this is a very long jacket, and it's farther than the bow. And you see that there's no support. And so we put a final X location of negative with a negative value. And here's the wireframe view. Again, here is the length of the skidways. And then you see that the final X location has a negative value, and therefore that jacket on those lower elevations is not supported. Okay, so that is how we would use those options on that on the loadout command for the automated installation tools. Now I'm going to take a brief view of how to set up for the ballast sequence. In loadout part 2, we're actually going to go into more detail as to what is what the steps are. So here again is that report of the restraints. Again, I altered this so that it fits on the screen. It's actually a much longer report. So I separated the starboard nodes and the port nodes. And here, for example, is how we would transfer loads to the barge. Okay, so with Moses, we work with load groups, and for this 10. We have just recently finished a video that goes into much more detail as to how you would pick these loads and what they represent on the barge, and then what the format should be as to how you, for example, how you pick which values to put for a minus L dist, and then how to define the nodes. For now, I have defined some nodes on the starboard side and some nodes on the port side where where the load is on the barge. Okay, I have added some distance to each one of these loads because I'm assuming that there is some skid shoe length. Okay, and I have also named, giving each one of these separate weights a name. That's what the -CAT option is for category. I went ahead and made the pair, gave it one name. So you see those that I have highlighted, even though they're on nodes 305 and 303, I named them both 305. Okay, part of that load is on the starboard side and part of it is on the port side, and I want it to be part on the starboard and part on the port, like it is from the report that is on the left-hand side. I want it to be on the port and the starboard side because I am going to be ballasting. So when I design my ballast sequence, right, if there is some imbalance between port and starboard, I want to be able to ballast that out. Okay, so I don't want to list during loadout. So that's how I would make my load group in my data file. Now during the analysis itself, I would have also asked for some reports. Okay, so we see there that right now I'm focusing on this 7,268 kilonewtons. So during the analysis itself, I would have asked for the category status report. And these two loads that I am focusing, 305 and 303, which I just happen to name 305, I would make sure that when I review my categories that it shows that 7,268 kilonewtons that the components add up to. And of course I would check all of the other ones as well. Another check that you would want to make is to make sure that the sum of all of the forces is being represented. So here at the total, you see the total on this report, but then there's also the total on the for example, the total is 31,789. So if you sum up that column that is listed as Z, you will also get this value that's reported with load group. And here, this Bunsen wave report also shows the ballast. Now, we are going to talk about what is needed for ballasting. And again, in my next video, I'm going to go into much more detail about this. And basically, for each stage, you are going to have a very similar set of commands, meaning the command structure, the command sequence is going to be pretty much the same for all of your stages. You're going to apply the load, okay, you're going to change ballast, you're going to confirm that you have equilibrium. Even if you ask the program to suggest a ballast condition, And the program is pretty good about suggesting a ballast condition that is at equilibrium. I still go ahead and ask for equilibrium. You just need to check. Now in this command file that I have a macro called repsum, and that creates a set of standard reports that I like to include in my output file. And we will be looking at those more closely in the next video. And also when we do our strength and longitudinal strength and bending moment. So another thing, part of this repsum macro is that you can also communicate with the yard in different ways. Okay, so one of the things that you're going to have to communicate with the yard is the ballast sequence when the pump turns on, when the pump turns off, when you are ballasting, when you are deballasting. Okay, there are many ways to communicate this. For example, this is a loadout stage 10, and you see that that heavy part of the jacket is on the midship of the barge. Okay, so just by looking at this picture, you would say, oh, there's a heavy part going onto the midship of the barge. Probably if there's any ballast in those compartments, that ballast is probably coming out because that big load is coming on. So one way you can communicate this to the yard is with figures such as these, where you indicate ballast or deballast via a color. And it should be coming up soon. And here we go. So here is the ballast condition. I have indicated blue as ballast, and that wheat kind of brown color is deballast. So you see, when we looked at the picture, just the side view, we thought to ourselves, oh, that water's probably coming out of the midship compartments, and for this stage it certainly is. Being able to make this type of picture that comes as part of the macro, it comes in the sample loadbal.dat file, and that is part of the files in the sample directory. And here is that macro. You can go ahead and look at it after the video. Okay, the other part that you sometimes need to consider about how you are communicating with a yard. A lot of times, for example, that buoyancy and weight report that we looked at, it had the ballast condition. The ballast condition, it had sounding, and then it had percent full, and it had the weight of the ballast water. Okay, when we're talking to the workers on the yard, they probably cannot measure the weight of the ballast water inside the compartment, right? And they probably also cannot. It's not easy for them to measure the percentage full. It's probably easier for them to measure the sounding. If they know a lot, if they have a lot of information on their pumps, they can probably measure how much water is added. Okay, by knowing how long that the pump was turned on. Okay, so we can also communicate to Moses in these ways. So with the ampersand compartment, a lot of people like to work with percentages, but of course you can always make the report in soundings. You can always define the amount of water that is in the compartment, or you can define how much water you're going to add. And of course you can do the sounding. You can also work with the ullage. Okay, of course we want to make our reports so that the yard workers can easily work with them, right? It's easier, right? Our job is a lot easier when our crew works as a team. And so we can certainly help along the way by actually working with commands that we know talk to us and make our answers easier to communicate to the yard. And we will be covering this again in more detail in the next loadout video. And then with all this information, you see that there's also the section that's big of commands, lines 45, that talk about moment. So this is how we get our longitudinal strength and bending moment. And this, of course, makes the assumption that we have the section modulus for the barge. And that concludes the video section of the presentation. And if there's any questions now, James, we can start them, and I can start the demonstration section of the webinar.
So yeah, please do send some questions through if you've got them in your mind. I've got one question through that's asking about the deflection and the loads as we bring the jack up out. Are we able to account for the barge deflection as it ballasts and takes on the load?
Okay. With the these files that I have that I'm showing you, these are the automated installation files. We assume we do make the assumption that the barge does not deflect. There because this wasn't, one, my video was intended to be an introductory. Two, usually people do the ballast sequence separately from the jacket strength analysis. I do know of companies who have made their own macros, and they do take into account the barge deflected shape. So that they're, for example, if for whatever reason, if your barge deflects, let's say 10 centimeter, and therefore your structural load case would include the loss of that support, you can go ahead and make macros to do that. What I'm presenting here today does not include that. It has separated the jacket structural analysis from the barge sequence, and the barge sequence would include the deflected shape of the barge. Okay, I wanted to just quickly show you some of these files that I presented in the video. Here is the set of files as I started off with. Here, remember, our first analysis was with a gap distance of 10. Okay, and here is the log file. Oh, because I put them here. Here is the log file that command file generated, and you do see this section here that I'm going to highlight. That was part of the video. This is where it shows a distance in between each one of the node sets. So remember, the nodes are on the launchways. Okay, please keep in mind that I did this for a jacket. Okay, whenever you do a loadout, you probably are going to have some set of skid beams. Okay, it was easier for me to show a lot of this on a jacket. You could also do if you're going to load out a jack up, you probably have a port side skid beam and a starboard side skid beam. If you're going to load out other equipment, you probably have a set of skid beams. So you would just need to tell Moses the name of the nodes, and of course there's a format as to where you start and end, and then Moses does all of these measurements for you. And here is this section of the log report was part of the video. And as you see, Moses tells you which nodes are on land. So remember position 1, they were all on land. Position 2, so here's position 2, and we see that one set of nodes is in the gap. Okay. And then position 3 is when a first set of nodes are on the barge. Okay, and then this continues until the last position or event. Here we are, position 14. So here's position 13 and 14. Position 13, there is one set of nodes in the gap, right? And then position 14, all of the nodes are on the barge. That's what makes it our last position. Moses automatically made load cases for each one of those positions. Here we are, time to generate load case, and one for each position. Okay, here's where it's solving the structural matrix. Gives us a little bit of warnings. Significant figures lost. For right now, I do not worry about 3.0 significant figures lost, because that has something to do with the size of the jacket, the loads that I'm looking at. I usually 3.0 significant figures lost. I might go look at that joint 2016, and then usually this isn't very alarming, but it's still worth looking at the size. Maybe see if maybe a fixity got changed, but usually 3.0, 3.3, you don't worry about too much. Just kind of review. That's why it's still a warning. Here's when it's actually solving it, converged in 2 iterations, and then time for post-processing. Okay, I added a lot of other post-processing because I wanted to show you some of this post-processing. So here we go. So this is the output. This is just a summary of the model size. Here are some program defaults. Okay, here it tells us the specific gravity of water, the acceleration of gravity, water depth. Okay, so maybe for loadout, some of these are not as important that we know, but these still are the parameters that were used. Here's the external piece summary, gory summary for part jacket. Okay, so this is how much the jacket weighs. If you are converting this file from SACS, of course you're going to want to make sure that the weight and buoyancy report match up. Here's a summary of the leg compartments. Okay, so this is making the assumption that this jacket will eventually be upended. And it does for the A side legs and the B side legs. Okay, so here is the how much ballast can fit in those legs. Okay, later on, it's assuming it can do a load, it can do a upend. Here's a summary of where the valves are. Okay, so here is the connector geometry. Okay, so all of the connectors that start with a B belong to the barge, and then later on we're going to see a lot of connectors begin with an L. They are connectors on the land. Okay, and the reason I'm showing you this is because later on when we actually look at the restraint report. Okay, so here's buoyancy and weight, connector forces. Okay, so this is when it starts off the connector forces if they were all turned on, right? But will not all be turned on. Either the barge node has to be turned on or the land node has to be turned on. Okay, so here's a restraint envelope. Okay, so because I added to this output, there's a couple of restraint reports. Remember, okay, so this first one is envelope. So envelope just means the highest and the lowest that was registered. Okay, because these connectors are either on or off, so the lowest will always be 0. Okay, so here's the land and the barge. Okay, and perhaps this is, if you are just looking for the extremes, perhaps this is a good report. A lot of people like to also look at them. I'm just going to speed on down to get to the reports that I...
Sorry, Georgina, can I
Yes.
interrupt again?
Yes. Yes, Jane.
Sorry, just had a topical question from before. Can you talk about how the loss of a support is included in the analysis?
Oh, yeah. Okay. So let's see here. I have load case 11 and I have load case 13. What? Other load cases did I do? 14 here. If I can get two files on my screen. Here is load case. Okay, so here's case 13 and here's case 14. Okay, so case 14 has all of the supports active because they are all on the barge. You see here it says all on the barge. Now for load case 13, we lost the support of 505 and 503. Okay, so I'm going to try to scooch that over. See if we can scooch that over. Okay, so here is load case 14, and if we see we're looking for 505. Let's start with concentrating on 505. Okay, so for 14, 505 has on the barge has 2,268 kilonewtons. Okay, and it has been turned off for the land. Okay, so that was 14 because 14 has them all active. Now, if we go up to 13, you see here under the column it says case, it says LOA 13. If we go all the way up here, again, we were concentrating on 505. When we get here to 505, we see that they both have been turned off. Okay, so that means that on the jacket, right, on the jacket node J505 for load case 13, right, that force is 0. So that would be a loss of support. And then down here for load case 14, so that is taking that support of 2,268, and that's how it accounts for a loss of support.
And look, while I'm interrupting, perhaps I can take you back before we asked about the deflection and stiffness of the barge.
Yes.
The second half of that question, stiffness of the jacket. Is the stiffness of the jacket accounted for in the load calculation?
Oh, the stiffness of the jacket, when we make the load case, okay, so what I'm showing you here is the restraint report. When we make the load case, we just take off that support. When you do the structural analysis of the jacket, yes, you can get the deflected shape of the jacket resulting from that loss of support.
And sorry to follow up on the previous question, rather than when the support goes through the gap, what about loss of a support through a mechanical failure?
Oh, okay. For that, okay, so the files I'm showing you right now, no, they do not automatically take that into account. We would have to make up another set of files where we simulate that loss of support.
Okay, so it is possible, but not configured in this run file.
Correct.
And one further question on structural loads.
Yes.
Are we able to account for not just loads from a structural model, maybe some point load from the rigging that has been manually inputted? And can the reaction take that into account?
Okay. Manual, having a hard time visualizing. Are we talking about maybe if you're sliding it with strain jacks? Are you trying to simulate the pull?
I think that's the interpretation. Yep.
Yeah.
So we're pulling on the jacket from a winch, strain jack, something.
Okay. Yeah. The okay. Yeah. For these set of files, no, I did not. That's not included. We could get another set of files where we could just input that strain. For example, the winches. We could put those in just with pound L set. I have a frequently asked question about pound L set. A lot of people when they use pound LSET, they believe they have to use the letters L, S, E, and T. That's actually, LSET stands for load set, but you get to pick the letters. So it could be pound, winch, if we wanted to, for example, what we're talking about right now. We could put them in as pound winch. But the concept would be the pound LSET command. Okay, so the other thing I wanted to, so here you all see that this is gap distance 10. And then part of the video, I also did, remember when the project had asked us to increase our gap distance to 15. Okay, so I did one with 10 and I did one with 15. And I have this already set up. So if we look at the comparison of the output files, so here is the output file for our gap distance of 10, and then here is our output file for our gap distance of 15. Okay, and if we go to hold on. Load 10. Okay, so here's load we're concentrating on stage 10. So if we, so here I have on the right-hand side with the gap distance of 10 and on the left-hand side with a gap distance of 15. And remember, we were concerned that there was not a set of nodes in the gap. But if we go ahead and look at what you can see that there is a change in the support conditions. For example, even just this first one that we see, 505, we have a difference of about 200 kilonewtons. But if we keep on going, we will see we will see that there is a set of nodes. For example, let's see here. Where is it? Right here. 303. So you see here 303. For our gap distance of 10, which did put the load onto the barge, right? We see that 3,439 kilonewtons of active support. And then over here on the left-hand side where we have increased our gap distance, we see just during 0 because it is in the gap. Okay, so I just wanted to go ahead and illustrate that, how you can get that. And how did I get these reports? At the end of the command file, I added these commands. So you go back into the structural post-processing menu, and you ask for a restraint load, and then you tell it which load you are interested in. And then you can also ask for just the code check for just that load case if you are just interested in the structural analysis of that one load case. We try to always give you an option on how to control your output. Here I'm just showing how you can control your output via load case name. We are working to be able to give you more of the output via command-rated values. We have also added an option that you can now save a lot of the pre-formatted reports. You can not the formatted part, but just the data part. You can now save them to SQL. A lot of people like working with SQL, so you also now have that option. With the comma-separated values, of course, you can always bring those into Excel. But here I'm just showing you what your options are in the structural post-processing part. And it looks like we're hitting the top of the hour. Is there more questions, James? That's kind of what I was going to conclude with. Oh yeah, there's something coming in. Great.
The question is, when will When will Moses provide a GUI for the users?
We are believe me, we are working, I hear you. We are working on it. There is now a GUI for modeling the outer hull structure. And we're working also on a GUI to do these types of standard command files. So we're going to start with these automated installation tools, and hopefully we'll continue from there. But right now, we do have a GUI for modeling, and our next step is to do some sort of interactive tool for these standard types. And I know I'm using the word standard kind of loosely, but the automated installation tools, I'm calling those standard. We are going to make a GUI for those types of analyses. Thank you so much.